The purpose of this video is to go over methods for differentiating and integrating data in Excel. There are basically two approaches. I'm going to talk very briefly about the first one, and then we'll get into a little more detail on the second approach. The first approach is going to make use of this sample data here. So let's say we've plotted time and velocity, and we have this from, let's say, an experiment of some sort. So I've plotted this here, and I've used a linear fit because I have reason to believe that that is a proper fit for this data. And how that works then is with the linear fit, we say that the velocity happens to equal 177 times t minus 115, and that is in centimeters per second. So one way to handle this is, let's say I wanted to take a derivative of this to find the acceleration. I can say a sub x in centimeters per second squared, let's say. I would have to just show you this briefly. Subscript on the x to make it look like a subscript, superscript on the 2 to make it look like a power, make them both bold. And if I wanted to take a derivative of this, I say, what's the derivative of 177t minus 115? And you take the derivative of that with respect to time, and it just equals 177. So there's really nothing you actually have to do here. I'll use the double click method that fills that in, and I will center that. And so from looking at this fit, I say, okay, the acceleration is constant, and it is 177 centimeters per second squared. I could also plot the position, let's say x per centimeters, and now I have to integrate this. So the integral of this is going to equal the initial position, so I would have to have some sort of an initial x naught. Make that a subscript, and let's just say I'm going to set x naught equal to 0. So I would say here that I'm going to enter, when I integrate this, the integral is going to be that initial x naught, that's the constant integration, so that's going to equal f1, so I'll just do the double dollar sign to fix that. Then we'll have minus 115, the integral of that is going to be minus 115 times t, so I'd go over here and select cell B5, and then I would have 177t, so the integral of that's going to be 1/2 times 177t squared, so I would add 1/2 times 177 times t squared, so I'll select that and square it. And I'll use the trick here, double click, and I'll center all that data, and I will also just give it 2 decimal points there. Okay, this is showing the time, velocity, acceleration, position. I could plot any of these. Let's say I wanted to plot the position. So I could select these 2 columns, insert, and maybe because this data is now exact, it's based off of a fit. So maybe I will show it connected with lines, and that's what I would get there. So this would be the position as a function of time. So the alternative method, which is actually the more relevant one for this lab as well, is that we want to show how we could do the same sort of thing, but instead of using a fit, we want to work directly with the data. So let's say I want to start with the derivative. So a derivative is basically like a slope. So if I look at any 2 data points, I can basically calculate what is the slope between them. And then I will associate that slope with the mid-interval time. So the first thing I need to do, I'm going to start a column over here, is I'm going to have a heading called t-mid for mid-interval, and I will put a subscript on the mid and bold it and center it. And so what I want to do is for every 2 times, I want to calculate the time in between. So let's say I start up here. So the first one is going to equal, I'll open parentheses, I want to add cell B5 to cell B6, and I'm going to divide by 2. So the mid-interval time between 0 and 0.05 is 0.025. So I can drag this down, and I'm going to drag it down all the way here just to make a point. So if you notice, so the second time we have 0.05 and 0.1, so the mid-interval time is 0.075, and so on. But if you go down to the bottom, you'll see that suddenly the time drops. And the reason for this is if we look at it and click up here, now we're adding the mid-interval between 1.25 and basically nothing. So what that's telling me is that I can't actually have a mid-interval time where I don't have the second time point represented. So I need to actually just get rid of that one. So when we deal with mid-interval times, we're actually losing one time step or one position because we always have to look at pairs of times. So I'll center that as well. Now, to take the derivative, again, I want to calculate the slope. So I'm going to put in an equation here for slope. Actually, so let me, just to save time, I'm cutting and pasting in the heading. Okay, so the slope now is going to be the rise over the run. So the rise, so it's going to be something divided by something. So I've got open parentheses divided by open parentheses. So it's rise over run. Now the run is the time interval. So in the denominator, for the first entry, I can put B6 minus B5. So that will be the run for the first entry. The rise is going to be the second value minus the first value in the vertical axis direction. So in this case, that would be C6 minus C5. So what this is saying here is that 317, that would be the slope of these first 2 points here. So it's the rise divided by the run. It's a positive because this is a positive slope. So I'm going to double click there, and that will give me fill in all these values. And there are a lot of significant figures here, so I'm just going to decrease this down maybe just to 1 like that, and center this. Now, if we plotted this, which we can do, insert, I'm going to plot this as a scatter. This looks like a big mess here. And if we go back to our original, the value should be 177. It should be a constant. But 177 is kind of in the middle of all of this mess. But what we're seeing actually is we're picking up all these slight differences in these slopes along the way. So this is what happens in this particular case when we take this derivative. Let me delete that. So now let's say I want to numerically integrate. I can numerically integrate by looking at the area under the curve, or the area between the curve and our function. So we basically want to calculate the area of kind of a trapezoid shape. So it's going to be the base times the height. So the base of the area is going to be the time interval. So let me type in. So it's going to be a parentheses times a parentheses. So it's going to be base times height. And again, we're integrating this data, this original data, this velocity data. So the base is the time interval. So the time interval for the first segment is going to be B6 minus B5. So that's the base. Now the height is actually the average value between the pair of data. So to get the average, I want to add these two values together and divide by 2. So I'm going to add, I don't know if this will make it more clear or less clear, but in these parentheses, I'm going to put another set of parentheses divided by 2. So within the first set of parentheses, I'm going to now add these two values together. So I'm going to add C5 plus C6. So if we look at this, we have the base, which is the time interval, times the height, which is the average value of the 2 points. So in this case, we get a negative value because we're on the negative side of the axis here. If I take this and double click, once we reach about 0.6 or so, it's going to start becoming positive. And we see that here at 0.675. Now we have starting to have positive values. And I will reduce the number of decimal points. Now, before, we're not actually done, and this is not completely correct here, because all we're showing is the area under the curve, so to speak, for each pair. In order to actually get the true integral, we have to add the previous value of the area under the curve in. So for example, this minus 5.23, I have to add, I'm going to change this, put a plus sign, I'm adding the previous value of negative 5.95. So I'm going to click up here on G5. So this first entry, G5, it's only the area under the curve, or the area based on this average of these points. The second segment, I calculate the area under the curve, and then I add it to the previous one. And the third one, I would calculate it and then add it to the previous two, and so on. So what that means is that there's a difference between this first entry and the second entry, and all the subsequent entries are going to be the same, basically, because they all have something to look to behind them. So this, by adding this through here now, I have actually determined the area under the curve, or the integral, based on this data. I can now plot this by selecting these two columns, insert, and we get something like this. And this looks very similar to what we got before on the other side, or the first sheet, when we integrated the curve fit. And if you notice, the integral looks much nicer. The integral of the fit looks much nicer compared to the numerical integral than the numerical derivative did. If we forgot what the numerical derivative looked like, I will plot it again, and I will now connect the dots. And so this was what the derivative looked like. So the integral looked much nicer than the derivative did, and that's very common. So these are two different methods for dealing with derivatives and integrals that originally start with discrete data points.